Hey, thank you, AWM Pittsburgh chapter, for inviting me for the talk. Today, I'll be talking about one of the project I did in my PhD. It was a joint work with Shihui Shai, Dr. Shihui Shai. The topic is numerical analysis of a corrected Smagorinsky model. So, corrected Smagorinsky model is a turbulent model. We'll get into it in a minute. So in this project, what we do is we develop and do numerical analysis of the turbulence model. We try to show how to extend a classical model for turbulence that was at a statistical equilibrium. Now we extend it to non-statistical non-equilibrium, okay? All right. Do you see my next slide? So it's showing my next slide, right? Guys? Okay. So what is a turbulent model? In our daily life, even in the fluid flowing through like a water faucet to chemical reaction in the engine that propels the plane, everywhere we see the turbulent effects, right? You can see this, this is a cigarette. So the smoke coming out of the cigarette, maybe for a certain period of time, you see laminar flow. But when it's creating some eddies and we see that the turbulence going on there, okay? So in general, if you want to understand the turbulent flow, most likely one of the well-known equation is Navier-Stokes equation. We know of that is it comprises of the two equation. Here you can see one of them is you can see that it's called continuity equation, and then next one is called momentum equation. Okay, so together as a couple, they serve the purpose. So we see that it's a high moment of convection is here happening, and then these Reynolds number are basically the ratio of these two, terms. Whenever the Reynolds number stays in the this value less than 2300, we see it's the laminar flow. One of the example of laminar flow could be the water in a just water in a glass. You can think of it like a laminar flow. Then whenever the Reynolds number is in between these variation, these numbers, then we can call it like a transition happening. And then whenever it reaches greater than 4000, we call it a turbulent flow. So using this number, we kind of can tell that whether this flow is a turbulent or not. So if you want to create a turbulent flow out of this equation, we pick the Reynolds number to be more than 4000, then we can decide it's a turbulent flow. This equation is called famous Navier-Stokes equation, and in our problem, we are going to so these are some, and again, some of the application why we really study turbulence. You can see in the list that it's a very complex and challenging aspect of fluid dynamics, and wide range of application happens, right? One of the common nature, you can see that flow of rivers, atmospheric condition, ocean currents, blood circulation, all these things you can do, weather prediction and all. Okay, so in many engineering project, they involve like turbulent flow, like fluid transport in pipeline, combustion in physics, engine, whenever the physics people do, and then heat transfer in the industrial system. So a lot of application of turbulence we see in our real life, and they are very intricate and very complex to study. So as a numerical analyst, our goal is to have some kind of progress in terms of this complex geometrical thing structure. We try to understand them. So turbulent flow significantly influences heat and mass transfer in various systems, and understanding how turbulence affects different processes is very crucial in designing efficient system. Okay, if you are working in a biotechnology, if you know the nature of the fluid you are working with, it's kind of get easier how you set up your technology, how you set up your lab, for example, for the work you are doing. So understanding turbulence is important. That's why we are doing numerical analysis of a turbulent flow in our research. All right. One of the another motivational picture you can see, it's a famous von Karman vortex street. So mainly the picture in the above you can see is taken in, I think, if I remember it correctly, is it in Japan or somewhere in Rishi Island? Okay, so they took this picture like a bird eye view of this picture, and you in laboratory you can simulate this kind of vortex happening. If you take a flow over a cylinder with just run number 100, you can simulate kind of this structure that you can see in the above picture is the real picture and the below picture is the simulated picture. So there is a similarity you can see. Okay. So accurate simulation of fluids for a high Reynolds number is very, very challenging. Okay, when the Reynolds number get higher, you see it becomes a chaotic behavior. It gives a turbulent flow. So accurate simulation is very, very challenging. So any progress in this matter is good addition for the scientific community. Any progress you can do through your research is one kind of addition to your your contribution to the scientific community. So in my project, for this specific project, we did a formulation of a new model. So kind of we get this new model from the NSE, but I'm going to show you how we get the new model, and then I'm going to show you like some basic properties that we proved, not going in details. Just if you read my paper, of course you will get details how these properties were proved, but I'll just go over the properties that we proved. We'll talk about some energy stability thing, and then numerically show the theorems that we have. Okay. So to formulate this model, what we did, we first took took a random initialization. That means in my initial condition, to solve an Navier-Stokes equation, we start with the initial condition, right? What if we have generated an ensemble of numerical initial condition, like we kind of have this omega type of thing. You see here is like a randomness. We are introducing some randomness in our initial condition. So for j many random initial condition, we will have j many Navier-Stokes equation we can solve, right? So how about we average them? So average can give us better prediction of what we are trying to predict of the fluid flow. So when we do the ensemble averaging of this thing, we see that there is a new term introduced in the system, which is like a fluctuation. Okay, so fluctuation, we refer it as a U bar, and then fluctuation will be the difference between the fluid flow and its ensemble average. Okay, and these are some technical things, just Reynolds stress tensor. You don't have to pay so much attention on it. Usually it appears in the system because of the averaging, because of the sum properties of averages. It appears in our system now. So whenever we try to do in our product, that means we try to do integration by parts by multiplying by the U bar with the NSE, we come up with this equation. Okay, so these are some basic setting. You think of them as a basic setting. We have some ensemble of initial condition for the NSE. The goal of the turbulent model solution is to approximate for most likely forecast. So we have to have like generate finite number of realization and average them. We are doing that. Okay, And after ensemble averaging, we see that NSE give a non-closed system. Okay, in our NSE, we see a non-closed system now. Now we have to have it a closed system, and that way we need to introduce something so that we can, have some kind of representation of this term, okay, in our main model. That's how we are modifying the NSE model. Okay. So this first term is the rate of kinetic energy here, so it means that uh, this means that flow due to viscosity, and then these extra terms, that is what for the turbulent fluctuation. This is responsible for the turbulent fluctuation, and this is just the right hand side is just the energy input. Okay. So here this negative fluctuation U bar will mean that energy is transferring back to mean. Okay, energy is transferring back to mean. Next, so before we do the next formulation, we need to know these two basic things that were already established. I think a paper written by Dr. Layton with his former students, where like under this assumption, Bushinsky assumption, turbulent fluctuations are dissipative on the mean, and this EV hypothesis, that dissipativity can be modeled by this term. So we already know this assumption. Using these two assumption, you see I have cited here like Dr. Layton and Lanjiang. They have proved this theorem. Okay. Now, if you consider that ddt of u, this term, to be 0, we call it statistical equilibrium. Okay. But if you are turning this off, you are kind of not getting a non-statistical situation like what's happening there. Okay. Excuse my cat. She's screaming. Okay, so usually all the eddy viscosity models are based on these two assumptions we have. Now, if we are turning this off to be 0, we are actually having no representation of this term in our actual NSE model. So we need to, we don't want this to be 0. We want to model something in our model so that it represents this term. Okay, that is the goal. So we don't, so we are extending the Navier-Stokes equation to have non-statistical equilibrium kind of state. So we are not going to turn this off. We are not going to set it is equal to 0, or we are going to have some kind of representation of that in our model. So what to do then? Based on this assumption, if you put this 0, we have a model and we call it classical Smagorinsky model. So this is not the model we have. This is just another classical Smagorinsky model. They also turn off this term. Okay, they have this. This is their eddy viscosity model. Now the W here just representing, the average of NSE solution. So instead of writing again and again U bar, I'm just considering it just W, and is the average of the pressure I'm selling is Q. So if you compare this equation with the NSE, this is the extra term coming up. So this is called classical Smagorinsky model. Not the model I am talking about. The model I am talking about, we will get it by doing some algebraic calculation. For example, in the Smagorinsky, nu t is written as this, but there is a Kolmogorov-Prandtl relation. The relation says that nu t is the turbulent viscosity is this. Okay. Now, if I write them equal to each other, I have an expression k prime is equal to this. Okay. So after algebraically solving this from these two equations, we have a new term which is called like like K prime is equal to this. Okay. So why the next slide is not coming? Okay. Okay. Now comparing these two, we have that K prime is equal to, so we have this equation for nu t, we have this equation for nu t from Smagorinsky, and then we just multiply by mu and divide by mu to kind of have a similar form like here. You see mu L square root of K prime, and here you have a mu delta. Delta is also like a mesh width we are considering like L. So if I compare these two, I see that K prime is equal to exactly this. Okay. So ddt of this can be written as ddt of the K prime of this, and we kind of work backward way so that we can have a representation in the variational formulation of this. So if you know that this is a variational formulation, then this term should come in the model. So if this red term is our new term in the model. Okay. So the difference between classical Smagorinsky model and the corrected Smagorinsky model is that we have this extra term. Now, if we track back this term, what is representing? We track back this term, we represent that this, right? The one usually in the statistical equilibrium case, people write that is equal to 0, that they don't represent this nature. Okay, but in our case, we are trying to have a representation of this term in terms of this. And this suggests that our model will ensure to kind of have, or not exact representation of the exact flow, it's very hard, but better turbulent flow. It will represent the better nature of the turbulent flow, because in real life turbulent flow is very chaotic, right? So we are hoping that our model that we established will be able to capture a phenomena called backscatter. Backscatter is a flow of energy coming from fluctuation of the flow to back to the mean flow. Okay, so this representation usually failed by the classical Smagorinsky model. Okay, so we want to see if the corrected one are able to capture that phenomena. The phenomena name is, again, it's called backscatter. In the term is backscatter, but it's mainly saying that a flow of energy coming back from fluctuation to mean flow. All right. Now this is our model, and if you are a numerical analyst, you know that we need to check some theory. We cannot just claim something is true, false, but without checking some facts. So one of the things we first do is we try to check if the energy is bounded, or all these things. So this slide is just all the thing I talked so far is just under one slide. This is my governing equation. All right. And then this is my governing equation, and then my big question arises that whether if my can represent. So if you look at this equation, the first equation is again continuity equation, which shows the conservation of the mass and incompressibility of the fluid. And the second equation shows conservation of the linear momentum. And if we compare with the NSE, we can see that this term is new and this term is new. But this new term is Smagorinsky model. This new term is a Smagorinsky model. We are okay with that. But the red term, the red one is the newest one in the corrected Smagorinsky model. All right. And nu is kinematic viscosity, nu t is turbulent viscosity, delta is the length scale or mesh size. So question, can it represent a flow of energy from unresolved fluctuation to the resolved mean velocity? Okay, because if it can, then it is something new we are trying to do. Otherwise, NSC would have been okay, Smagorinsky would have been okay. So, so big question we are answering is that can it represent a flow of energy from unresolved fluctuation to back to the mean? Answer is yes. That is what we are claiming. Okay. Unresolved means very, very small scale. Okay. Okay. And to see small vorticities, we actually need very smaller scale, which is mathematically impossible. Okay. That's why we need to see this representation if the flow of energy coming back from unresolved fluctuation to the resolved mean velocity. All right. So first thing we do is energy estimate. So okay, so basic properties of the model, we are trying to figure out what are the basic properties of the model. All right. So in the basic properties of the model, this theorem is you can easily prove if you have taken numerical analysis course or something. Usually you multiply with the test function and then you do integration by parts. So when you do that, you will have this theorem. Okay. So model kinetic energy of mean flow per unit volume. Okay, so this is model kinetic energy. This is a model kinetic energy, and then you have energy dissipation here. Okay, this is always positive. It reduces the accumulation of this kinetic energy, so it kind of balances. Okay, it's energy and then it's energy dissipation, and the extra so here we are having the right hand side. This is energy input. Okay, rate of energy input to the mean flow per unit volume. Okay, so now we show that I did not write the all theorem statement, but just the gist of the theorem, what we proved. Okay, so we proved unconditional stability of the W. We show that model kinetic energy is uniformly bounded. Okay, so if you want to see details of the proof, stability of the W, uniqueness proof, and even the model error and error of the semi-discrete case, that means the solution between the actual solution, error between the actual solution and the semi-discrete solution. All this error estimate you would be able to find in the paper written by me and Dr. Shihui. So basically it's saying that if we do if we look at the stability of the W, we say that model kinetic energy is uniformly bounded. We also check that time average model energy dissipation also bounded. We show the uniqueness. Okay, we show the model error and the semi-discrete error case. All these estimates can be found in our paper. I didn't want to bombard you with the equation here. Okay. Okay. Now next. Next is, whenever I'm clicking, it's not going. Okay. Okay, next is I'm just showing you a fully discretized form of the variational formulation. First, I'm using backward Euler here. Those who are not familiar with finite element method might seem very, very weird, this term, but I'm pretty sure some of you are in the audience know it, what they are. They are variational formulation of the PD model we had, okay? Weak formulation, you can think of it like a weak formulation. We are looking for weak solution kind of thing. So later on we have applied another time discretization method, which is called linearized Crank-Nicolson. So basically the finite element in both, but for the time discretization we chose backward Euler, also linearized Crank-Nicolson. Okay, we have a reason for that, by the way, why we chose these two. Because backward Euler has numerical dissipation. Okay, because of backward Euler, the system has more numerical dissipation in it, and that's why even though we are aiming to see the backscatter, we will not be able to see if we use backward Euler. So our goal is to see backscatter, as I was telling you guys earlier. So when I check the energy stability for the fully discrete case, if you look at the difference between this theorem and this theorem, only term is missing is this term in the Crank-Nicolson. So this term is the numerical dissipation term. So this comes as a penalty of using backward Euler, the second term I'm talking about. But if you look at the Crank-Nicolson, we don't see that term is not there, right? When we prove this theorem, we don't see this term in the Crank-Nicolson case. And that will make a huge difference in the numerical test, okay? So next. Every time I'm clicking next, it's not going. I don't know. Sorry, guys.
I think you can use the arrow keys in the PDF.
I'm trying to use it. It's going down, more down, just missing one slide.
At the bottom, there is a arrow, downward arrow.
This one?
I can't.
Oh, I see. This one.
Yeah.
Oh, okay, okay. Thank you. So these are backward Euler and this is the Crank-Nicolson one. Okay. I still feel like it's missing one. Okay. Anyway, so this is a usual test. Everyone first tries if their algorithm working right or wrong. Any numerical paper you write, you first usually check if your code is working right and everything. That is basically a checking error. Okay. So you have a kind of known exact solution, and then you compare your result with the numerical solution. And because of the backward Euler, it is expected to give you order 1. So you have kind of order 1 in your answer. Okay, so that means the code is nice and you set it up for the other test problem. Okay, so next we are going to test something that is our domain is like a offset cylinder. So if you look at this, it's like a uh, um, wait a minute. So 2D offset cylinder. So it's like a the outer circle is fixed, and then and there is a force, body force that rotating this flow. Okay, so once you set it up, this is your domain, and you try to see the backscatter phenomenon. So you are trying to observe these quantities in your test. So first quantity is called model dissipation. This is denoted by that. Second quantity is effect of the new term. That means the new term in our characteristic Smagorinsky model gives us this effect, and overall eddy viscosity term. Okay. So now our goal is to check if the model dissipation is negative or not. Usually it can be positive or negative. When positive, it meaning that it aggregates energy from mean to fluctuation. But we are looking for something if that can show us negative model dissipation in that sense that energy is being transferred from fluctuation to mean. Okay. So um, only we notice that in the picture, if you look at this model dissipation picture, so for the backward Euler, the blue line is always at the up, but for the Crank-Nicolson, you see sometimes you are getting negative values as well. So even though it's a good model, backward Euler is failing to show us because of it has extra numerical dissipation in it. So it's kind of giving more extra I mean, it's not helping us in some ways. So like it's hiding those negative values. So Crank-Nicolson is telling us that yes, your model is okay. Is showing the flow of energy from fluctuation back to means. So looks like this corrected Smagorinsky model is sensitive to the time discretization method we choose. All right. So because Crank-Nicholson has no numerical dissipation, it gives us nicely, nicely capturing the phenomena we are looking for, where backward all are failing. So we also checked some streamline plot. You see a lot of chaotic eddies here, but at the time, as the time goes, they are smoothing out, so they are becoming like a equilibrium. So we see their flow becomes smoother at it approaches the statistical equilibrium. Then we also checked the Taylor microscale. We just compared how the character Smagorinsky model and the Navier-Stokes and the standard Smagorinsky model, how the Taylor microscale changes, So we see that corrected Smagorinsky model has large microscale. So it models the backscatter. Average length scale of the corrected Smagorinsky model is larger than the NSE and SM. Um, to see the difference more closely, we take a zoom version of the picture. It's like a relative length scale. We took relatively zoomly. We want to see that. We see that almost like um, regular Smagorinsky is, you can see the Taylor microscale is here, relative length scale, and where almost characteristic Smagorinsky is almost double here. It's like a zoom version of the previous picture. So overall, our takeaway from this problem is that this model captures the backscatter phenomenon, and it is very sensitive to time discretization method we choose. That's why our next project was, how about we choose a variable time step problem, and then for variable time step problem, how it reacts this model. So you can next work of this paper, you can see it here, and this paper is published in NMPD journal, and the next paper is published in IJMAM journal. All right, that's all. If you have any question, you can ask me.